Hello, my name's Dan Munk. I'm an irrigation, soils, and cotton farm advisor for the University of California Cooperative Extension in Fresno County. And today I'd like to visit with you about soil moisture monitoring and the utilization of soil moisture during a drought. To start my talk, we're going to talk about the water balance, or sometimes referred to as a water budget approach in irrigation management. And then we'll move to a discussion of plant available water and its importance in irrigation scheduling. And we'll talk more specifically about tools and methods for collecting soil water data and interpreting those numbers, all in the context of farm irrigation management planning. If we look at a field water balance approach to irrigation scheduling, we have the following equation. And basically it says that the change in water content, or delta W, is equal to the inputs of water into the system minus those things that actually reduce water content of the soil. Things that are positively influenced are irrigation, so inputs are irrigation, precipitation. In some cases, a shallow water table might exist, and capillary rise would then be a positive or an input to the system. And then things that take water away from the system or out of the system would be considered things like runoff, or deep percolation losses where water moves below the root zone and is no longer available to the crop. And then actual crop evapotranspiration, denoted here by ETA. In many of the systems that we work with in irrigated agriculture in California, precipitation is not that great of an input or an influence, particularly during the cropping season. It may be an influence in the winter or spring months, but that's not that much of an issue later on in the season. And if you don't have a shallow water table, capillary rise is very much a smaller, reduced or no component to the positive inputs of water in soil water. Similarly, runoff and deep percolation are often minimal losses to the system. And if we calculate with those reduced elements, if we look at the large majority of changes in soil water content, they occur because of irrigation inputs as well as evapotranspiration, the removal of soil water. So talking a little bit more about ET and the estimation of ET, this is often a primary approach for doing some water management planning on farm. And basically the ET of the crop, or ETC, is equal to a reference crop evapotranspiration, which is often calculated through automated CIMAS stations that are based throughout California, and then multiplied with a crop coefficient, or a KC, from published values that have been developed from previous research or work on your farm. ET-based information can be very useful in establishing a water management plan or scheduling plan early in the season. Here I'm describing or denoting a cotton water use element that's basically divided up into weekly events, and it gives you an idea of what water management or what water use is occurring with the crop on a weekly basis. It relies on an accurate but changing crop coefficient throughout the season. But in reality, many years we don't have identical data, and some years are warmer than others, and therefore we actually have a higher crop coefficient earlier because the plant canopies are present at different times based on climate and weather, which is illustrated in this element here that shows not only that ETO is very different from year to year, but also crop coefficients will change for a developing crop under these different environmental conditions. So what we need are tools to verify whether or not our water management plan, developed oftentimes by ET-based information, is useful. And so plant-based methods such as pressure chamber can be a very practical tool for evaluating or verifying whether or not the water management plan that we have going forward is appropriate. Plant-based measurements often can be direct indicators of plant stress, but they're not indicators of water use. And while these indicators can be quite useful in scheduling irrigation events, there are some problems with using plant-based methods alone. For instance, the response time might not be timely enough, and they're not practical for all crops. So we need additional tools to verify that our ET-based planning activities are helpful. One of the ways in which stress is related to soil water availability is by looking at a couple of different soil types that I have here on the graphic. Basically, we're seeing two different soils that have two very different water availability contents to them. And the sandy soil you see accumulates after an irrigation event, begins to accumulate water stress much faster than a clay loam soil. This is simply because of the differences in plant available soil water in the system that we're monitoring. So we want to do something more than evaluate methods and verifying methods for ET-based scheduling by not just plant-based approach, but if we can, it's more common to have soil-based methods available to us that can be used for this purpose. So I'll spend most of the talk now just talking about some of the soil water elements that are important in irrigation scheduling. And basically, if we look at the soil volume, approximately half of that soil volume is pore space, half is mineral material. And in that pore space, if you can imagine a flood event and flooding the soil would result in raising the water content to approximately 50% of the soil volume. And if we can further imagine then that water draining from the system, we can see that the water moves from a point of saturation up at the top of the diagram here, and after gravity has had an impact on drainage, it comes to a steady state at what we call field capacity. And field capacity is going to be different depending upon the soil type, soil texture, structural elements, etc. So this defines the upper level of plant available water. If we have a crop on that same field and after drainage, then the crop begins to remove soil water, it comes to a point where basically the crop can no longer extract water from the soil, and because of the remaining water is unavailable to the plant. And we call this level the permanent wilting point, sometimes also referred to as the lower limit of soil moisture. And if we take the difference between the field capacity value and the permanent wilting point value, we come up with an estimate of what plant available water is for that soil. Now this is important because it helps us get a sense for what the volume of water is on any given location in any given field. Now it's very common to use that plant available water as a guideline for irrigation scheduling. For instance, many crops use a 50% depletion percentage. That is, after half of the plant available water is extracted, an irrigation scheduling event is then initiated. But these values differ depending upon the crop's capacity to take on stress, or the crop's need to have more frequent irrigations. So in the early season, stored water, we want to identify whether or not stored water in the soil is adequate. And this brings us back to the question of the seasonal water use plan. Seasonal water use planning can be an effective way of distributing water throughout the season and anticipating water before it's actually used. But if we look at residual soil moisture in soils and seasonal contributions, part of that residual moisture comes from rainfall. And the rainfall, just like some of our ET that we described earlier, is fairly non-uniform from year to year. Some years we might have, or some locations, we might have soil moisture, residual soil moisture peaking simply due to rainfall events. But this, again, is not always the case, and something which is an important component of our soil water management. Residual soil moisture can also come from water that remains there from a previous crop. So if we had a well-irrigated crop, for instance, that did not have a lot of water extraction following the final irrigation, there's going to be a tendency to have a lot of residual soil moisture in that soil as well. The other element of our seasonal water balance is considering the current crop and the crop depth of influence. So in other words, if I'm in an annual cropping system, if I'm planting a new crop, you're going to want to know what the current root depth is going to be for that crop at any particular time, and that depth of influence will be important in terms of estimating whether or not residual moisture is going to be an important factor in the whole season water balance. So we want to be able to create access to the plant for available water, which will vary depending upon the root depth and rooting density. Rooting depth and distribution for any given crop is soil dependent. And I illustrate that here in the following graphic, in which we had cotton planted pretty much the same date at 3 different locations and 3 different soil types. And what it shows is that particularly as we move into the later season, we see that the actual rooting depth for some soils is quite shallow, in this case about 3 feet or so in mid-August. However, in other soil types, that rooting depth might be as deep as 6 feet or so. So we're extracting different amounts of water and have access to different amounts of water depending upon the site and location. We can also get a first approximation of rooting depth based on the crop type. And here's an example of information that's available for a wide range of permanent and annual crops to give you a sense for what the rooting depth is for each of those crops. So let's talk now about soil moisture monitoring methods. And probably one of the easiest and one that most people are familiar with is simple soil probing, in which we can get a good estimate or general idea of the profile moisture content. But this is a qualitative estimate. This gives us an idea of whether or not there's water available in surface or subsurface layers, but it really doesn't tell us how much water might be available. So we move to more specific monitoring methods and monitoring tools, such as tensiometers. Tensiometers have been around for many years and use a basic principle in which a cylinder is inserted into the soil. The tip is a porous ceramic cup, and then it's sealed at the top with a cap that has a reservoir and also a vacuum gauge. And as that instrument is placed in the soil and in direct contact with the soil, it begins to equilibrate, and the tension that develops is based on the wetness or dryness of the soil. In the graphic down below, you can see where an instrument basically started out at day 1 following an irrigation. It increased until the water matrix potential reached about 90 centibars or so, and then suction was broken on that, and we basically had a reading of 0. Other moisture monitoring methods include the use of electrical resistance blocks. And these resistance blocks are of different types. Some you might have heard referred to as gypsum blocks, and others, such as Watermark, are available on the market and give a measurement of electrical resistance as the sensor is brought into equilibrium with the local soil moisture, soil water environment. Neutron probes are also being used. They're used often by researchers and consultants alike. They basically have a americium beryllium radioactive source that throws out a small amount of radiation, and that particle radiation that interferes with water molecules. Those fast particles that are emitted interact with water and become slower molecules, which are then picked up by the detector. So the more water, the more slow-moving particles are out there, and the higher the reading for the detector. And this is how this operates in terms of identifying and returning a value of volumetric soil moisture to the user. Dielectric sensors are another approach or method that are used, and this exploits basically the dielectric constant of the soil and how it changes with changing water content. There's a number of these probes available on the market. So which method is best? Well, it really does depend on the application and the data being targeted for the decision making that you want to make. To give you a little bit of a sense for some of the different methods and advantages and disadvantages, tensiometers, they measure soil matrix potential, and it's fairly localized, that measurement. It's fairly sensitive in high water content ranges. However, with permanent crops and other agronomic crops where a significant dry down occurs in the soil water, the measurement is basically no longer available after about 90 centibars. And so you need to use these in very moist conditions. Resistance blocks, on the other hand, have a much wider range of soil water limits, and the readings mimic soil water content changes in a larger or wider range of water contents. Neutron probe, on the other hand, one of the downsides is that it's relatively expensive and requires licensing and monitoring. But it does monitor a larger soil volume of about a half a cubic foot and provides a good volumetric water content reading with depth. Irrigation consultants and large farms often use these systems. Dielectric sensors, as I mentioned, there are a wide range and type of measurements out there, but some of these systems are fairly sophisticated. They have continuous readout from multiple depths, and wireless connections are available for some of these systems, making near continuous data streams possible. So let's talk now about a couple of examples, one in which we have a high available water and available to the crop and stored soil water, and one that has a lower amount. If we look, for instance, at a deep-rooted cotton crop on a heavier soil, let's say a clay loam soil, for instance, we know that storage is about 2 inches per foot. If we recognize that this is a deep-rooted crop and that moisture is effectively removed from 6 to 7 foot depth, we can estimate that about 10 inches or more can be contributed from that soil in terms of from the beginning of the season to the end of the season, which accounts for approximately 30% of the water available to the crop. On the second example, take for instance the more shallow-rooted corn crop on a lighter soil. And let's say that soil water content is more like 1.4 inches per foot. If we look at a 4-foot section for depletion, we still can see that there's a difference of about approximately 5 inches from the beginning of the season to the end of the season, translating to about 17% of the crop water use. Neither of these situations is the water stored by the soil insignificant. In the case of cotton, which uses about 28 inches of water, and in which a grower might apply about 30 inches of water to account for some of the non-uniformity, we only need to apply about 20 to 22 inches of water in season based on high levels of stored soil moisture. Similarly, with a shallow-rooted crop, while we don't make up nearly as much of the water from stored soil moisture, we still have a situation where the in-season applied water recommendation would be lower than that of the actual ET scheduled or estimated at the beginning of the season. In terms of how this might go into practice in a real field, consider the graphic here, in which A is the graphic A refers to or is a representation of the estimated amount of water consumed, the ET, for a crop, for a given crop, and where B was an attempt to account for stored soil moisture content. So this allows us to develop estimates of water contributions from irrigation by actually reducing and changing the shape of that curve based on the fact that stored soil moisture will then be a component. And our irrigation management can then be aimed and directed toward that new guideline based on stored soil moisture. So let's talk a little bit about sensor placement. What is the goal of your monitoring plan? If the goal is to have specific and discrete measurements for triggering irrigation events, sensor placement should be considered in that light. In another light, the sensor may be useful for long-term water management, and we might want to have more information about water storage characteristics of the soil and use that information for the planning, longer-term planning, as we've discussed earlier. We want to place these sensors in an area of primary irrigation water influence. What I mean by that is that we want to place them where irrigation water is reaching that sensor on a regular basis and where there's an active root zone that's taking up that water on a regular basis as well. It's generally useful to monitor the upper root zone and the lower root zone to verify soil volume exploited by the plant. Deeper placements may be needed for crops that are deficit irrigated or that have more infrequent irrigation events, such as furrow or flood type irrigation. In the case of sprinkler and drip irrigated sites, a more shallow placement tends to be what is more useful. In terms of establishing soil moisture target values for irrigation scheduling, consider this. Even in drip irrigated systems, most crops are irrigated only after a water deficit occurs. So in other words, we want to wait until there's a significant deficit before we initiate irrigations. This will minimize deep percolation and some of the losses that we have as a result of deep percolation losses. Based on experience, early season targets may differ from the late season targets. Early season targets might tend to be more shallow, and more weight might be placed on those shallow readings as opposed to later in the season, when deeper soil moisture readings might be more appropriate for targeting irrigations. Target soil moisture values are used to minimize crop stress or the over-application of water. And ET of the crop, the data that we develop early in the season, can assist in determining the target. So if we know what the estimated crop removal is through an ET estimate, we can actually develop a schedule in which a specific deficit is used to schedule irrigations. And soil moisture monitoring can help establish these values or these deficits. Plant-based monitoring methods that are used in concert with ET and soil moisture devices are often target-based and can be used to assist in developing soil water targets. Having that experience or that additional information can increase the confidence at which soil water targets or triggers are initiated for irrigation scheduling. And finally, irrigation system type can play a role in those targets. If we have very frequent irrigation, certainly we're going to be scheduling irrigations more frequently, and we're going to have lower deficits. So that's all for now, and I thank you for your attention.